Welcome everyone. Today is the third lecture on nonlinear dynamical systems. This is between Madhu Belu, that is me, and Harish K. Pillai. So we had just begun with phase portraits of second order systems last week. So consider this differential equation x dot is equal to Ax, in which A is a 2 by 2 matrix, and now we are trying to see various situations that arise depending on whether the eigenvalues of A are real or complex, whether they are repeated or distinct, whether A is singular or non-singular. So the eigenvalues of A, let me recap, are the roots of the determinant of Si minus A, and this eigenvalues decide the key features. So we will begin assuming that A has no eigenvalue at 0, which means A is non-singular. In such a situation, the origin in the plane is the only equilibrium point. The different types of equilibrium points for this situation are center, which we had just begun seeing, the node, in which case it can be a stable or unstable node, then there is a focus, a stable or unstable focus, a saddle point, and some other situations which, for example, when there are repeated roots and when there is one or more eigenvalues at 0. Those are the situations we will see separately. So a stable node. A node can be stable or unstable. So what is a node? It is a situation when A has two distinct eigenvalues and both are negative. In such a situation, it is called a stable node. The other situation when A has both real eigenvalues and positive is called an unstable node. To analyze this, we will quickly see how the vector field looks for this particular A. So look at this figure. This is not the same example that is there on the slide, but it explains what is a stable node. So this is the x1 axis, this is the x2 axis. What this says is, if we are along the x1 axis, then because x2 component is 0, when A acts on such a vector, again the x2 component is 0. That is the significance of a diagonal matrix A. And similarly, along the x2 axis, x1 component is 0, and these diagonal entries being negative imply that that is also along the x2 axis, the arrows. The relative distance, the relative length of the arrows certainly depends on the x1 and x2 components, but then as far as this picture is concerned, as far as qualitative study is concerned, this explains how the various arrows are. So the origin, the unique equilibrium point, appears to be a stable node. It is a node, all arrows are directed towards it. There is no rotation involved because the off diagonal elements are equal to 0 and all arrows are directed towards the origin. This is what we saw as a stable node. We will later see that it is asymptotically stable in the sense of Lyapunov. Let us quickly see what an unstable node is. Take the same A, except that the diagonal elements have sign opposite. Again, because of the diagonal nature of A, along the axis, the arrows are parallel to the axis themselves. With careful attention to the arrows, whether they are in the positive direction of x1 or negative direction of x1, it will be away from the origin because of the positive sign of the diagonal elements. The off diagonal, for points which are not along the x1 axis, by just superimposition, because this is a linear vector field, by superimposition, for example, at this point, the x1 component of this arrow can be obtained by this point, and the x2 component of the arrow can be obtained by the arrow at this point. This is the net arrow. So this is what we can obtain by superimposition, because A is a linear map, because we have a matrix that decides the vector field at different points. So before we go to stable and unstable focus, we will quickly see what diagonal has got to do with what we are studying. So if we are given with a general A, let's say 4, 5, 6, 7. So I am just guessing the various elements, and suppose the entries are such A11, A12, A21, A22. Suppose the entries are such that this matrix is diagonalizable. It may not be diagonal itself. In other words, A12 and A21 might not be 0, but if it is such that there exists a non-singular matrix T such that T inverse AT is equal to a diagonal matrix, then by choosing the columns of T as a basis, we still have this decoupled vector field. Decoupled vector field like we saw for x1, x2, we can see it is not along x1, x2 axis anymore, but suppose this is one column of T1 and suppose the other column of T2 is like this. In general, the two columns need not be perpendicular to each other. Suppose this is eigenvector V1, this is eigenvector V2, and suppose this eigenvector corresponded to the eigenvalue lambda 1 and this corresponding to eigenvalue lambda 2. These are the x1, x2 axes. These are not the eigenvectors. More generally, eigenvectors are vectors V1 and V2 which may or may not be perpendicular to each other. These eigenvectors are corresponding to eigenvalues lambda 1 and lambda 2. So if lambda 1 is negative, then we can draw the arrows just like we had drawn for a stable node, and if lambda 2 is also negative, these arrows also can be drawn towards the origin, and the other places the arrows can be filled again, as I said, by superimposition. So more generally, if A is diagonalizable, we have two directions called eigenvectors along which we can draw the arrows either towards the origin or away from the origin, depending on whether lambda 1 is negative or positive respectively. In which case again we are able to decide whether the node is a stable node or unstable node. Our assumption till now has been that both the eigenvalues are of the same sign. When they are of different sign, that is the next thing we will see. Sorry, before we see the situation when the eigenvalues have opposite sign, we will start with what a center is. So this is a situation when A has purely imaginary eigenvalues. Take for example this, because of this particular form and in which the diagonal elements are equal to 0, the eigenvalues are plus minus 3 times j. So this corresponds to, as I said, rotation about the origin either in the clockwise or the anti-clockwise direction, which we will decide very quickly. So take a point along the x1 axis. Suppose this point is equal to 4, 0. The point on the x1 axis has x2 component equal to 0. When matrix A acts on this, we get minus 12, sorry, 0, minus 12. We see that we get a vector which is parallel to the x2 axis and in the negative direction. So this is the arrow at the point 4, 0. Similarly, when we draw these arrows at different points, we see that we have a rotation in the clockwise direction. Every point except the origin is, if we start at any point, then we are continuously rotating, and it turns out that the vector A times V is perpendicular to the vector V itself. So if we are at any point V, then the arrow at that point AV, that is perpendicular to this, and we see that this is nothing but what corresponds to pure rotation, in which the velocity is perpendicular to the radius vector. The clockwise or anti-clockwise just depends on whether the sign, whether we have a plus sign here or a plus sign here. So this other example that is there on the computer corresponds to an anti-clockwise rotation, because we have a negative sign here and a plus sign here. We have an anti-clockwise rotation for the second example of A, and both the A's correspond to periodic orbits with the number 3 indicating the frequency, but since we are interested only in a qualitative study, the precise value of the frequency is not significant. Another important point to note here is we have a collection of periodic orbits. For each initial condition, the radius, the distance from the origin decides which periodic orbit it is. The x1, x2 space itself is made up of periodic orbits which are all very close to each other, which form a continuum. From each initial condition x1, x2, there is a periodic orbit, unique periodic orbit going around it, and if we go a little away or little closer to the origin, then we have another periodic orbit. So, for the situation that A has imaginary axis eigenvalues, we have a continuum of periodic orbits, and for a linear system it is not possible to have isolated periodic orbits. As we saw in one of our introductory lectures, that we can have isolated periodic orbits for a nonlinear system, but for a linear system, when we have periodic orbits, it appears that we have a continuum of periodic orbits. In other words, if we start from a slightly different initial condition, then it is very unlikely to be on the same periodic orbit. If we are on this periodic orbit starting from this initial condition, unless we perturb the initial condition to another point on the same periodic orbit, the periodic orbit is going to be different. If it is from this initial condition, then this initial condition corresponds to a different periodic orbit, which means a different amplitude, even though it is the same frequency. So, this is the inevitable situation with linear systems when we have periodic orbits. The next type of equilibrium point we will see is when A has complex eigenvalues, and these eigenvalues are not purely imaginary. So, take for example A equal to in which the diagonal elements are equal to -1 and the off diagonal elements have opposite signs, one is +2, one is -2. So, this we will call is a stable focus. As I said, the off diagonal elements cause rotation about the origin. Each of these cases A is non-singular, hence the origin is the unique equilibrium point. So, let us take an example of a particular point and decide where the arrow is when we are at this point. So, this point for example is 4, 0. When A acts on this, we get -4, and in the and below we get +8. So, this is a vector which is like this. There is -4 component towards the origin and 8 component along the positive x2 direction, because of which we have this. So, when we take different points, we see that it is no longer perpendicular to the radius vector, but it is directed inwards. So, every point it turns out that we have some rotation and eventually the trajectories come to the origin. For example, at this point, if we draw the arrows at different points, all trajectories seem to be approaching the origin, even though they do not approach the origin in finite time. So, each trajectory, these trajectories do not intersect, but they all approach the origin and they reach the origin only asymptotically. So, this is a stable focus, and unstable focus is also very easy to see, only that the diagonal elements have positive sign. Now, all the arrows are directed away from the origin. Also, the rotation has been reversed because the signs of this and the previous example have been interchanged. So, here is an example where the arrows are all directed outwards. So, we have at any point we have trajectory that is going away. Different points are all going away from the origin. So this is what we will call an unstable focus. Finally, we will see what is a saddle point. So the situation when A has real eigenvalues, one positive, one negative. Again, for simplicity, we will start with the diagonal case. That time, because it is diagonal, again we have a decoupled nature of the phase portrait. So we see because A is equal to -1 0 0 plus 2, along the x1 direction it is approaching the origin, while along the x2 direction is going away from the origin, and any other point is a superimposition of these two features. So we see that unless the x2 component is equal to 0, which means we are along the x1 direction, all trajectories are coming towards the origin. Any other point where the x2 component is non-zero, while the x1 component is still decreasing, the x2 component is going to blow up. Why? Because the solution to this differential equation x1t x2t, because it is diagonal, can be easily written as e to the power minus t times x1 0 e to the power plus 2t times x2 0. So unless the initial condition has x2 component equal to 0, the x2 as a function of time is going to grow exponentially. On the other hand, if the x1 component is non-zero, it is going to decrease and eventually become close to 0 asymptotically. So this is what we will call a saddle point. The question arises, is the saddle point stable or unstable equilibrium point? We see that while the origin is an equilibrium point, for very small perturbations about the origin, trajectories either come to 0 if they are along the x1 axis, or they do not come to 0 if they are not along the x1 axis. In any case, there are certain very small perturbations such that the trajectories, when they begin from that perturbed initial condition, do not approach the equilibrium point. So in other words, there exists. So this is the symbol for there exist. There exist initial conditions these initial conditions are close to the origin. Close to the origin. What is significance of the origin? It is an equilibrium point. There exist initial conditions close to the origin such that the trajectories are not coming back to the origin. So we have, in fact, the trajectories are growing. Trajectories are becoming unbounded. This is precisely the property that decides that the equilibrium point, the origin, is an unstable equilibrium point. So the saddle point is an unstable equilibrium point. It is not an unstable focus nor an unstable node. That equilibrium point is just an unstable equilibrium point. So what is saddle about this? So the graph of the Lyapunov function, we will come back to this later. This graph in the 3D plot looks like the saddle of a horse. That is the reason that this equilibrium point is called a saddle point. So before we go to the other situation where there are repeated eigenvalues or one or more eigenvalues at the origin, we will just quickly recapitulate what was done. So we have seen the situation when there are distinct real eigenvalues, when both are positive or both are negative, or when they have opposite signs. Then we saw the situation when the eigenvalues are both complex, in which case if they are on the imaginary axis, we call it a center. This is the one that corresponds to periodic orbits, and we saw that we will have a continuum of periodic orbits. For the situation that the eigenvalues are complex, if they are on the imaginary axis, then it is called a center. When the real part is negative, we call it a stable focus, and when the real part is positive, we call it an unstable focus. So whether it is stable or unstable depends on the real part of the complex eigenvalues. Now the next situation, last situation that is remaining to be seen is when there are repeated eigenvalues, and also the situation when one or more eigenvalues are at the origin. Coming back to the matrix A, when there are repeated eigenvalues, that time the matrix A may or may not be diagonalizable. So, suppose we have a repeated eigenvalue lambda 1, and if A is diagonalizable, that is when we will like to put a 0 here, and if A is not diagonalizable, then we put a 1. So, this is called the Jordan canonical form for the case when there are repeated eigenvalues and A is not diagonalizable. We are restricting ourselves to the 2 by 2 case, and this is the Jordan canonical form for the case when eigenvalues of A are repeated, but A is diagonalizable. So, what is the significance of a diagonalizable matrix? We saw that the eigenvectors are so called invariant directions. In this particular example, x1 and x2 directions are themselves eigenvectors. If we are along an eigenvector, then lambda, depending on lambda 1 being positive or negative, the arrows are directed either away or towards the origin. So, this is the case when lambda 1 is greater than 0. Let us restrict our study for that situation. The x2 direction is also an eigen direction, is also an eigenvector, and because lambda 1 was positive, it is again directed away from the origin. So, we see that the eigenvectors are the invariant directions. What is invariant about it? If the point starts along an eigenvector, because the arrow is also directed along the eigenvector, we continue in that direction. So, there is no tendency to move out of an eigenvector. Let me repeat, eigenvector V is a non-zero vector such that AV is just a scaling of the vector V. So, we are interested in the first eigenvector V1, which is nothing but eigenvectors are not unique in magnitude. We can scale this vector to any number by any number and also get an eigenvector. So, it is a non-zero vector that satisfies this equation. So, this V1, if we are along this direction, if we are at a point V1, then the vector is parallel to the vector V1 because of this particular equation, and hence the trajectory will remain along that particular direction. If we start here, then there is no reason to come out of the x1 axis. Similarly, if we are here, we will remain along the x1 axis. Similarly, here x2 also being an invariant direction, being an eigenvector, it continues to be along the x2 axis. So, we see that this particular complex plane contains certain invariant sets. What are those invariant sets? So, we will define the plane R2 is made up of invariant sets. So, what is this invariant set? A set S is called invariant. In this case, it is invariant under the dynamics of the differential equation x dot is equal to f of x. If we start inside this set S, then we will remain inside this set S for all future time. It is called invariant. Invariant means under the dynamics. Under the dynamics of f, if we start inside S, then x of t is also going to be inside S for all t greater than or equal to 0. So, that is the significance of an invariant set, that a set S, which could be a subset of the plane R2, or it could be the plane R2 itself, it is said to be invariant if the initial condition is inside S, then the entire trajectory is inside S for all future time. Hence, this is also called a positively invariant set. What is positive about it? Because we are interested only for positive values of time t, x of t is inside S. So, what are the invariant sets inside R2? If we have this differential equation, and let us take the special case when matrix A acts on the vector x and A is 2 by 2, which means x has two components. So, of course, R2 plane itself is an invariant set. Why? Because if it begins inside the set R2, there is no reason it will leave the plane R2. If the origin is an equilibrium point 0, the set S consisting of just the origin, yeah, S consists of only origin. This is also an invariant set. Why? Because if it begins inside this set S, because it is an equilibrium point, it will remain at the equilibrium point for all future time, and hence the set S is also an equilibrium, is also an invariant set. So all equilibrium points is an invariant set. For this particular case, when A is a diagonal matrix, for this particular A, there are some more invariant sets. So take the set S, which is defined as all the points where x2 is equal to 0, the set of all points x1 comma x2 such that x2 is equal to 0. This set is also an invariant set. Why? Because if we are along the x1 direction, because A was a diagonal matrix, x1 axis itself being an eigenvector, we see that the set S1, which is defined to be the x1 axis, is also an invariant set. Of course, the x1 axis itself contains the origin, which is also an invariant set. In other words, another set, let us call the set S2, defined as all points x1 comma x2 such that x2 is equal to 0 and x1 equal to 0, which is nothing but the equilibrium point, is an invariant set. But we are interested in some non-trivial invariant sets. For example, we could take x1 positive. This particular situation is along the positive x1 direction, excluding the origin. This is also an invariant set. If it is once inside the set S2, it remains inside the set S2. Consider S3, which is the same x1 comma x2, except that now x1 is negative. This is another invariant set which corresponds to the negative x1 axis. If the point starts here, then it is going to always remain on the negative x1 direction. So these are different invariant sets. So we are usually not interested in the equilibrium point as an invariant set. We are also not interested in the plane R2 as an invariant set, because these are the trivial invariant sets. We are interested in some more sets which are larger than the equilibrium point and smaller than the set R2, which are invariant under the dynamics of F, and the eigenvectors are examples of such invariant sets. Eigenvectors, the entire direction except the origin is also an invariant set, and the two sides of this eigenvector, one on the positive side, one on the negative side of the origin, also form invariant sets. So coming back to the case when A is diagonalizable, for that situation, as we saw, in some basis A already looks diagonal. So we have x1 axis, which is an invariant direction, x2 axis, which is also an eigenvector, hence that is an invariant direction, and it turns out that this invariance, this two directions being invariant, is not particularly related to the eigenvalues being distinct. For the case when A has repeated eigenvalues, but if it is diagonalizable, it still is a unstable node. Of course, in this case every direction is an invariant direction, every line through the origin is an invariant set, because the two eigenvalues are repeated. But for the situation when A is not diagonalizable, so let us consider the case when A is equal to 2, 0, but with a 1 here. This example of an A has only one eigenvector. The other eigenvector is what we want to call a generalized eigenvector. This A, which A are we dealing with now? We see that the x1 axis, if we take the vector v equal to 1, 0, AV is nothing but 2 times v. So, the x1 axis is the invariant direction and all arrows are directed away from the origin, but there is no other invariant direction. There is only one independent eigenvector, and hence if you take an example, let us say v is equal to 1, 1, when A acts on v, we get 3, 2. Let me check this. Yeah. So, for this particular vector at 1, 1, the vector has both x1 and x2 components of that arrow non-zero. So, we see that because there is only one independent direction, x2 axis is no longer an eigenvector, but there are these other arrows that cut. How exactly they cut? They depend on the particular form of the Jordan canonical form, but along the independent axis there is only one x1 direction. So, this is the significance of a non-diagonalizable A, that there is only one eigenvector x1 and everything else is emanating out of this x1 direction if it is very close to x1, but if it is along the x1 axis, then x1 axis being an eigenvector is an independent, is a invariant set under the dynamics of F, and hence it does not leave the x1 axis. So, this brings us to the final case when A is singular. When A is singular, there might be one or more eigenvalues at the origin. So, let us see the case when there is only one eigenvalue at the origin first. So, when A is singular, it means that there exists a non-zero vector x naught such that A x naught is equal to 0. This x naught is also said to be in the null space of the matrix A. The origin is always there in the null space, but when A is singular, there are some non-zero vectors also which are in the null space, and such a non-zero vector x naught is non-unique. Why? Because if we are given with x naught, then we can multiply x naught by a real number b and also get b x naught to be in the null space of the matrix A. So, all these points x naught, b x naught, any scaling of the vector x naught are all equilibrium points. Why? Because they satisfy the derivative of x at that point, evaluated at the point x naught, is obtained by A acting on x naught, which is equal to 0. So, we see that in this case all the equilibrium points are connected, they form a line. The null space, which is a linear subspace, in general they form a subspace, and in our case, because A has only one eigenvalue at the origin, they form a line. So, as we have seen in the beginning of this series of lectures, we saw that isolated equilibrium points is not possible for a linear system. For a linear system, the equilibrium points, as we have seen, happen to be in the null space of the matrix A. If there are some non-zero vectors in the null space, then they are all connected, they form a line. So, the isolated equilibrium points is possible only when we have a non-linear dynamical system. So, we have just begun seeing the repeated eigenvalue case. When A has repeated eigenvalues, A may or may not be diagonalizable. We will quickly review this part. So, when the eigenvalues are repeated, then they have to be real for the case that A is 2 by 2 matrix. If the matrix A is diagonalizable, then we have two independent eigenvectors. Then each eigenspace is an invariant subspace. Invariant meaning it is invariant under the dynamics of the system. But it is also possible that we have only one independent eigenvector, in which case other directions either turn towards this or turn away from this, depending on whether the eigenvalue is is positive or negative. So one can have a look at how the arrows look using champ command in Scilab or quiver command in MATLAB when A is singular. So take for example A equal to, in this case this is an example such that A x naught is equal to 0. This is of course not the only vector x naught that satisfies A x naught equal to 0, because any constant minus 5 times x naught also is in the null space. Also in the null space is also said to be the kernel of the matrix A. So what is the significance of this? We see that the x1 axis is an eigenvector but correspond to eigenvalue 2, and hence we will draw the arrows away from the origin, but the x2 axis are all equilibrium points. So each of the arrows have length 0. So if the x1 component is non-zero, then we see that the trajectories are having their x1 component increasing as a function of time, increasing with exponent equal to 2. But the x2 component is always going to become equal to 0 when A multiplies to it, and hence we see that these arrows are all parallel to the x1 direction first of all, and secondly along the x2 axis, because x1 is equal to 0 along the x2 axis, all these points are equilibrium points, they form a connected set. The origin is not the only equilibrium point for this example, but each of these points are equilibrium points. So this is what we see for the case when A has one eigenvalue at 0. The next example is when A has both eigenvalues at 0. This is again an example of repeated eigenvalues. So let us first take when A has two eigenvalues at 0 and when A is diagonalizable, that is when we have 0 here. So A is a 0 matrix. So the entire R2 plane is made up of equilibrium points. Any point x1 comma x2 is an equilibrium point. Why? Because what does this matrix say? X dot is equal to 0 times x, which is equal to 0 for any point x1 comma x2. So this is the less interesting case, but still this situation is likely. The other situation when A has repeated eigenvalues at 0, but A is not diagonalizable, is when we have this, for example. So in this case, we see that if we have vector x equal to 1 comma 0, then Ax is equal to 0. So the vector 1 comma 0 and all linear multiples of this x are in the kernel of the matrix A, they are in the null space of the matrix A, and hence the x1 direction is a set of equilibrium points. What is important about the x1 direction? They all have x2 component equal to 0. But if we take a vector v which is equal to 2 comma 3, in particular the second component x2 component is not equal to 0, this particular vector here, when A acts on v, we get something that is parallel to the x1 axis. So we see that the arrows look like this. They are all in increasing direction of x1 when x2 component is positive, and they are all along decreasing direction of x1 if the x2 component is negative. Why? Because A is this matrix. When A acts on a vector v, it gives us the second component of v as the first component of A times V. So, this is an example where we have only one x1 axis, which is the equilibrium point, set of equilibrium points, and every other vector is being turned towards either positive direction of x1 or negative direction of x1, depending on whether x2 component is positive or negative. So, this completes our study of equilibrium points for second order systems. We have seen the case when A has repeated eigenvalues, distinct eigenvalues, and when A has real or complex eigenvalues.